Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 3, describing, exploring, and comparing data. In the first sections, we focused on measures of central tendency, how to find the mean, median, and mode. We call them measures of the center. But in this particular video, we would focus most of all on the measures of variations. And usually measures of variations are it's about range, variance, and standard deviation. So for these sections, as we said, we would develop the ability to measure variation in a set of examples data by finding values of the range, variance, and standard deviation. We will develop the ability to interpret values of the standard deviation by applying the range rule of thumb to determine whether a particular value is significantly low or significantly high or neither. So it's extremely important to emphasize on the importance of standard deviation. Of course, we're going to use variance just to compute the standard deviation, but we're not gonna, it's not really useful, the variance, but we will focus on standard deviation. Key concepts, as we said, variation is the single most important topic in statistics. So this is the single most important section in this book. So these sections, as we said, we will present the three important measures of variations, range, standard deviation, and variance. But we're gonna say variance and standard deviation. That's very important to focus on. So these statistics are numbers, but our focus is not just computing those numbers, but developing the ability to interpret and understand them. Round of rules or for measures of variations, round of rules for measures of variation. When rounding the values of a measures of variation, carry one more decimal place than is present in the original set of data. So very important to verify this. The range of a data set is the difference between the maximum and the minimum data entries in the data set. So to find the range, what we need to do, to find the range, the data must be quantitative data. It's about the quantitative data. To find the range is maximum minus the minimum. So any data set we have, remember we have three measures of variations, range, variance, and standard deviation. We have three measures of the center. Remember measures of the center. We said it's mean, median, and mode. So we covered in the previous video covering chapter 3, section 3.1. Feel free to do it. So we said measures of variation. We said its range. B, its variance. C, its standard deviation. So if we ask you to find the measures of the center standard deviation, measures of the center, eventually you can add also the mid-range, even though we don't use it very often. So mid-range is the measures of the center. But range in itself is a measure of variation. So we said the range, anytime you hear the word range, is the largest data in the data set minus the smallest data in the data set, max minus the mean. So the range use only the maximum and the minimum data. Okay, you need to pay attention to this because it's not really very giantly helpful. The range, data. So it's very sensitive to extreme values. The range is not very resistant because the range uses only the maximum and minimum values. It does not take every values into account like the mean does, and therefore does not truly reflect the variation in all the data, right? We have the variance of the data. Let's say, for example, I'm gonna just pick up in, if suppose we have a data set, I'm gonna put a data set. If I have a data set like this, oops, data set. Let's suppose we have something like 1, 3, 3, 2, 5, 6, and 8. I take a random, find the range. Find the range. So for me, range, remember, you need to identify what is the maximum, the largest number in the data set, and what is the minimum. So for me here, I see the maximum is 8 and the minimum is 1. So we're gonna have 8 minus 1 is 7. This is the range. But for the variance, we're gonna see it different ways, right? Variance and standard deviation. As the measures of variation, the range has the advantage of being easy to compute. But its disadvantage, as we said, is that it uses only two entries from the data set. So two measures of variation that use all the entries in the data set are the variance and the standard deviation. So before you learn about these two, you need to know also what it means by the deviation of any entry in a data set. So we said variance of a data set of a set of values is the measures of variation equal to the square of the standard deviation. So if you know the standard deviation, then you know the variance. If you know the variance, then you know the standard deviation. We call a variance for a a sample S square of the standard deviation. We call the variance for a population sigma square. Okay, sigma square is a Greek letter. Sigma square, we're gonna use it for it. So the symbol is the lower case Greek letter sigma. Okay, remember this one is okay lower case. Can I say lower case Greek letter sigma, right? So that's what it means. Now, for the deviations, as we said, the standard deviation S can increase dramatically with one or more outliers. The unit of the standard deviation, I don't know why I put the standard deviation before the variance, but I know we're gonna go with, I'm gonna go that way for you, so you see what we're talking about. Let's do this one first. I don't even know. Okay, yes, definitely this one is come first. So we said for the standard deviation, okay, standard deviation of a set of sample values denoted by S. Okay, so remember we talk about as a measures of variation, one disadvantage with the variance is that its units are different from those of the data set, right? To overcome this problem, we take the square roots of the variance to get the standard deviation. So it's very important to get the standard deviation. So what we're gonna do in this case is to look for the standard deviation, the population standard deviation of a population data set of n entries is the square roots of the population variance. So if we know the population variance, usually, let's say for the variance, I'm gonna just put the formula for you for variance for S square when, remember that's about sample as variance. So S square sample variance. Let's do it properly. I want to do it cleaner. Sample variance, we're gonna call it S square. S squared, in this case, remember we do it for the sample. When you do it for the sample, it would be a little bit different because it's gonna be summation, we used that word before, xi minus x bar square over small n. Remember, in this case, x bar, okay, I'm not gonna put it there. We know that x bar is the sample mean of the sample, and is the sample size, right? And xi is each data values in the data set. But if you do it for population variance, you need to write those formulas. Some population variance, we use this lowercase Greek letter sigma square. So for sigma square, we're gonna use capital. Oh, sorry, that would be over n minus 1. So it's better you remember that's over n minus 1 when it's sample. But for population, it should be xi minus mu square over capital N minus 1. Of course, we have some other formulas you can use, but we're gonna start with this first one for the population. Okay, when you deal with population and when you deal with the samples, right? So sorry, we need to do it not over minus 1, only over n. This is remember the mean mu is population mean, and capital N is population size. Okay, population mean and population size. Okay, that's very important, right? Now, you know how to find the variance. When we deal with standard deviation, we said, the population standard deviation, just take the square root of the variance. If population standard deviation is sigma, you take the square roots of what you already know for the variance, like you do sum of xi minus the mean square over capital N. Sample standard deviation is simply S. You take the square roots of the sample variance, which is sum of xi minus x bar square over n minus 1. So for us, we said the standard deviation S can increase dramatically with one or more outliers, if the numbers are big, in a company where we are interested on employee salary. If you have most of your salaries range from 40,000 to 55,000, but you have the CEO with an annual income of 500,000, it will definitely affect the average, the mean, okay? And it will also affect, the variance and the standard deviation. The unit of the standard deviation S, such as minutes, feet, pounds, are the same as the units of the original data in the data set. The sample standard deviation S is bias estimator of the population standard deviation, which means that values of the sample standard deviation S do not center around the values of the standard deviation of, sigma, right? So for us, these are the formulas to find the standard deviation. I gave you that one. There are two different formulas that you can find the standard deviation. This is another one. So this is but at the same time, if you're looking for the variance also, variance S square, the variance S square can also be N summation of X square, XI square, add all the X's, square each X values and add them up together, minus add all your x and raise it to power 2 over n times n minus 1. So you can use that also for the variance, right? So The standard deviation is a measure of how much data values deviate away from the mean. So the standard deviation tells us how far we deviate from the mean. The value of the standard deviation, S, is never negative. You need to remember that. It is zero only when all the data values are exactly the same. Larger values of S indicate greater amounts of variation because we study the variations. Before we do a big examples, because standard deviation of the population, a different formula is used to calculate the standard deviation. So we said for the of the population, instead of dividing by n minus one as we do for the sample, for the population, we divide by n. As I said, I'm gonna do very simple examples to explain before we do those provided in the exercise. Let's suppose we have a data set. I believe I give you the data set already. Let's copy paste because I just give you one before. Uh, where is it? We're gonna take an examples. Let's take this data set, all right? I'm gonna copy this data set and put it there, okay? And for this one, we can ask two questions. A, find the measures of the sender. Find the mean, median, mode, and mid-range. I can ask you to do this. B, find the range, variance, and standard deviation. Right? These two questions. Now, how we can proceed to answer these two questions? Let's do this. We're gonna answer them both. All right, for A, we know the mean. We consider this one as a sample. I'm going to call it a sample data set, so do not compare it if it's, let's do it as a sample, not as a population. Usually they would tell you what it is if it's sample. So we're gonna say sample mean is X bar we use. Add all your data together divided by n. So meaning 1 plus 3 plus 3 plus 2 plus 5 plus 6 plus 8 divided by the number of data. How many data we see here? 1, 2, 3, 4, 5, 6, 7. We know n is 7, so we're gonna divide by 7. Adding all this data together, I believe it would give you 28 over 7. So we know the mean X bar is 4. So we know the mean. We can also find the median. So in order to find the median, we must reorder our data from the smallest to the largest. Let's try to reorder it. I'm going to put 1, 2, 3, 3, 5, 6, 8. We must reorder our data from the smallest to the largest. And the data that's all exactly in the middle is the median. So for us, we would consider the median as 3. Remember, the median is really 3 because it's exactly the same. Again, for the mode, okay, mode is the data that is repeated the most. What data you see repeated more than once here? 3. 3 is the data the data with the highest frequency is 3. With the greatest frequency is 3. Mid range, you need to add the minimum to the maximum and you divide by 2. Remember, the minimum, the smallest data in the data set is 1. The largest data in the data set is 8. So if we do 1 plus 8 over 2, that is 9 divided by 2 is 4.5. So we find the mean, we find the median, we find the mode, we find the mid-range. Now, next questions. B, they ask us to find the range. Remember, the range is simply the largest number minus the smallest number, which is 8 minus 1 is 7. So we know what is the range. The next question is to find the variance and the standard deviation. We know in terms of variance, because it's a simple, we're gonna call it S square. We know S square is sum of xi minus x bar square over n minus 1. Our problem, we don't know this. So what we're gonna do, we will use this data set to construct a small table where I would let me put a table here. It's always better to go to use tables, right? So we're gonna call this one x. I mean, what are the numbers? If I put 1, 3, 3, 2, 5, 6, 8. Now, our goal is to subtract the mean from each data and raised by pi 2. So, for example, we're going to subtract the mean from 1 power 2. I believe that's give 9. 3 minus 4 power 2, 1. 3 minus 4 power 2 is 1. 2 minus 4. Remember, 4 is the mean. Power 2 is 4, right? 5 minus 4 square is 1. Remember, 1 minus 4 is negative 3 power 2. Any negative numbers you raise to power 2, okay, that will give you a positive number. So because it's raised to power 2. 6 minus 4 power 2 is definitely 4. 8 minus 4 power 2 is definitely 16. Now, our goal, we are more interested in this case to the sum. So we want to know what is sum of x minus x bar square is. When you add all these numbers, I believe 9 plus 1, 10 plus 1, 11 plus 4, 15 plus 1, 16 plus 4, 20 plus 16, 36. Now we can answer the questions here. Sum of x minus x bar square would be 36 over n, which is, remember, number of data in the data set is 7 minus 1. So that gives you 36 over 6 is 6. So we find the variance S square equal 6. Also, they ask you to find the standard deviation. So the standard deviation is the square root of the variance. Standard deviation. All you need to do with the standard deviation is, we call it S, take the square roots of the variance. The variance is not very useful. So we use the variance just to find the standard deviation. Square roots of 6 is 2.449. So we know the standard deviation is 2.449. Now, we said there is a different formula you can use to compute the mean and the variance and the standard deviation. One of the formulas we said that you can eventually use, we know S square, which is the variance. We can use this formula, variance S square is equal to n times sum of x squared power 2 minus sum of no, let me remove the parentheses. Sum of x power 2, that's two different things, over n times n minus 1. First of all, if you add all these data, we're gonna find sum of x would be, let's add them all. If you add 1 plus 3 plus 3, 7 plus 2, 9 plus 5, 14 plus 6, 20 plus 8, 28. Now we already have the sum of x. We can raise to power 2, but we also need x squared. If we raise 1 power 2 is 1, 3 power 2 is 9, 3 power 2 is 9, 2 power 2 is 4, 5 power 5 is 25, 6 power 2 is, 6 times 6 is 36, and 64. Adding these numbers, we know sum of x squared would be what? sum of x squared. Two different formulas, but I'm pretty sure at the end the answer would be the same. That gives you 148. So if we use this formula, we're gonna have n is 7 times s squared. Okay, there is no power 2 in this one. Okay, yep, like this. We're gonna have what is sum of x squared is 148 minus 28 power 2 over 7 times 7 minus 1. Again, we're gonna have our s squared would be 7 times 148 turn 36 minus 28 power 2, 784 over 7 times 6, 252 over 42. So S, again, here S squared, the variance would be equal to 6. And you know the standard deviation is square root of 6, so which is S would be 2.449. Again, either formulas you use, at the end, answer would be the same. I take a very simple example to explain how that's work. Okay, that's very important. Take a very simple example to explain how that work. But for now, let's practice it in some real examples. But because as you can see, doing this manually would take forever. That's why in every examples I do here, I would go and perform another examples using Excel. Check my Excel files to find exercises where I would compute the measures of the center, measures of variations using Excel. So how to find variance, mean, median, mode, variance, standard deviation using Excel. Please pay attention and look for this video on the Excel files. All right. When I see these two examples, I'm gonna just do only one and leave every other exercises for yourself. I'm gonna do only A because, well, I do A. I only do A. Yeah, they said find the range. I'm gonna make it smaller because we need a lot of space. As you can read it from the beginning, let's go and make it 16. So I can put this one a little bit higher. Remember, our goal when you do these type of examples, it's very important to reorder your data from the smallest to the largest. But we don't really need that because they don't ask us to find the median. You need to reorder your data from the smallest to the largest if you're looking for the median or if you're looking for measures of positions that we haven't covered yet. Now, the range, the only thing you need to do here from this data set is to identify what is the smallest data values in the data set, what is the largest one. So we believe the smallest data in that data set is really 11 and the largest data is 87. So if you're looking for the range, we know the range would be 87 minus 11. So the range in itself would be 87 minus 11 is 76. So the range is not a very good measures of variation because it doesn't take into account all the variance. Now the variance, remember you need to look for the keywords. Are we dealing with population or are we dealing with, are we dealing with populations or are we dealing with a sample? Looking at here, they said find the range variance and standard deviation for the given sample. If they said sample, then we know the variance we're looking for is S squared, and that is summation of x minus x bar, that were, okay, x bar square over n minus 1. So we must find the mean. You cannot compute the variance and the standard deviation without the mean. We know the mean, sample mean here is x bar. We need to add all this data until the last one. and divide it by the number of data. They said 11 data here. So when you add all your data together and divide by the number of data, all right, we believe the mean is 47.8. 47.8. I must just verify and make sure this is the correct answer for this data set. The mean, yeah, I believe the mean is 47.8. All right. Now for the variance, again, we're going to construct a small table where we would do, it's better we construct a small table that actually we're gonna do the variance. Okay, we're gonna have x, the x we have 12, we have 12, 26, 46, 15, 11, 87, 77, 62, 60, 69. Because of technology, not a lot, we're not gonna do this all the times by hands, but unfortunately, to pass the class, you really need to understand how to do it by hands. First of all, you need to subtract the mean from each of these x values and you raise it to power 2. What we mean, you're going to do 12 minus 47.8, you raise it to power 2. 26 minus 47.8, you raise it to power 2. 46 minus 47.8, you raise it to power 2. 15 minus 47.8 raised to power 2. 11 minus 47.8 power 2. 87.47.8 power 2. 77.47.8 power 2. 62 minus 47.8 power 2. 60 minus 47.8 power 2. 69 minus 47.8 power 2. 61 minus 47.8 power 2. You can do it once in your calculator because what I'm most interested in is this answer. So what this one would be, I can definitely use my calculator to find this answer. Let's see how I can proceed to find it. Mm, Let's do this like this. I can do, of course, I'll show you. Oh my God. Okay, let's do. There's so many data that I can do. Can simply do. Let me grab my calculator. Um, 7,000. I mean, that's the final, the big numbers here. It would be 7,554. Now, what's the variance? Remember, the variance for us is this answer. So the variance would be this sum, 7,554 over n 11 minus 1. That make it 7,554 over 10. So we agree that's our beautiful variance, S square is 755.4. This is the variance. Now remember, standard deviation is the square roots of the variance. Standard deviation, S, is the square roots of the variance. Square roots of the variance. Meaning standard deviation S is the square roots of sum of xi minus x bar square over n minus 1 because we're dealing with a sample. So that means square roots of 755.4. So standard deviation to us, when you take the square roots of 755.4, it gives you 27.5. This is the standard deviation. We call this one the standard deviation, how far you vary from the mean. So how far you go from the mean is the standard deviations. Now, what does this data tells you? Usually ask you these questions. So because the Jersey numbers are really just replacement for names, they are the normal nominal levels of measurement, so the results are meaningless. So we don't really need to analyze, So I'm doing only one examples because all the other examples, the only thing that's matter to these, we ask you the exact same questions. Is like your tables would be longer, the deviations would be longer because you always need to subtract the mean. You always need to subtract the standard deviation, the mean from each x values, then you raise to power 2. So that's why you see, I would leave you with all these data, then you can do on your own. The only thing I would add more to this is the rule of thumb. So we're gonna talk a little bit about the rule of thumb because once you understand the standard deviation, the variance, and the range, you already covered what we call the measures of variation. Now, the rule of thumb, what it tells you, is a crude but simple tool for understanding and interpreting standard deviations, right? It is based on the principle that for many data sets, the vast majority such as 95% of sample lies within two standard deviations. So it's a rules of thumb, or we call it empirical rules. If you have, let's suppose this is your mean right here, this is your mean. So if we said this is one standard deviation, one standard deviation above the means, remember, we call this is mu is the population mean, and we have sigma is the population standard deviation, and both for population, right? For population. And if it was for sample, we're going to do X bar mean and S standard deviation. That's for sample, right? Sample, right? So we said that way, and we know if you go above the standard deviation 1 standard deviation, we're gonna call it one standard deviation, or you can go below the mean one standard deviation, or you go two standard deviation above the mean, or you go two standard deviation below the mean, or you go three standard deviation above the mean, or you go three standard deviation below the mean. But what the rule of thumb tell us in it is based on the principle that for many data sets, the vast majority is like 95% of the data lies within two standard deviation. That means the vast majority of the data would lies between these two, you know. So meaning, this stats would be about 90%, 90%, right? 90%, 95% of the data would lies between two standard deviations, right? So we could improve the accuracy of this rule by taking into account such factors as the size of the sample and its distributions, right? So we can sacrifice accuracy for the sake of simplicity. The concept of significance, because we're gonna talk about significance, the concept of significance that follows will enhance, like we said, rule of thumbs for identifying significant values. Significantly low uh, values are two standard deviation or lower. So here, significant. I need to avoid that. Okay. Significantly low. Okay. So we said significantly lows values are below this number, right? And significantly high, significantly high, two standard deviation or higher, and values not significantly between is neither. So everything that's fall between here, we said it's neither. Significantly neither. If we want to say significantly, we can say significantly neither, right? So very important to see significantly neither. Now, we understand this one is significantly low below or two standard deviation, significantly high above two standard deviations, and in the B, not significantly. So I'm hoping you understand this. Notation here, remember we said in terms of summary, if you want to see it the other way around, let's construct it. I'm going to construct a table in which I'm going to put population and I'm going to put sample. We know the mean the mean mean for the population, variance, and standard deviation. Let's put a table like this, and I would like you to keep that table forever because you're gonna need it if you ever work by hand. So this is how it works. The mean for a population, we call it mu. Okay, remember you add all your data and you divide by population size. And the mean for the sample, we call it X bar. We still do the same thing. You add all your data in the data set, you divide by the sample size, the number of data in the sample. Variance for the population, we call it sigma square. Remember, it is the lower case Greek letter sigma. So you subtract the population mean from each data, you raise it by 2, you add them up all together, and you divide it by capital N. And if it's for the sample, we call it S square. You do the same, you subtract your sample mean from each data in the data set, you raise it by 2, you add them up all together, you divide by N minus 1. You need to remember it's N minus 1. For the standard deviation, all you need to do is the same. You'd only take the square roots of the variance. Instead of having sigma square, you're gonna have sigma. You take the square roots of the variance, xi minus the mean square over capital N, or we call it S, square roots of sum of xi minus x bar square over N minus 1. All right, keep this table because that's something you're gonna need in the future. All right, we said important variations. As we said, the units of the variations are the squares of the units of the original data values. The values of the variation can increase dramatically with the increase of outcomes. The values of the variance is never negative. Remember that, it's only 0. I think we already covered this part, but we didn't talk about there are only 1 minus 1 values that can be assigned without constraint. With a given mean, we can use any numbers for the first n minus 1 values, but the last value will then be automatically determined. So with division by n minus 1 sample variance, S squared tend to center around the value of the population variance sigma square. With division by n, simple variance S squared tend to underestimate the value of the populations. Remember that? Now, the empirical rules is the same type of things we were trying to explain on the first one, but we let you to see what it is, because for the empirical rule, you know, we can say that at this point, many real life data sets have distribution that are approximately symmetric or bell-shaped. For instance, the distribution of men's and women's height, in the United States are approximately symmetric and bell-shaped, right? So for now, however, we can use what we call an empirical rule to help us to see how valuable the standard deviation can be as a measure of variation. This one, the empirical rule states that for data sets having a distribution that is approximately bell-shaped, the following properties apply. So we have that rules, we call it empirical rules, or you call these rules, usually a lot of people call it 68, 95, 99.7 rules. You give these rules two names, right? Because if you try to figure it out, it's very important when these guys develop what we call the empirical rules, you know um, for the data sets, that are approximately symmetric and bell-shaped, the standard deviation has these characteristics. So we said about 68% of all values fall within one standard deviation, like I did before. 99% falls within two standard deviation, and 7% falls within three standard deviations. So that's something very important for you to see. I'm hoping you can go over it, and we're gonna, of course, do one examples. Remember, we said if you have the means here, one standard deviation above the means, two standard deviation above the mean, three standard deviation above the mean. I use population here, or one standard deviation below the mean, two standard deviation below the mean, or three standard deviation below the mean. So if you are between one standard deviation, 68% of the data falls in this one. So for examples, uh, if we have the average income in a company $50,000, we are certain with a standard deviation of 5,000, we know if the average income in a company is $50,000 with a standard deviation 5,000, I mean, you can confirm using empirical rule that 68% of people working in that company has income range from 45,000 to 55,000. Or we can say 95,000% of people, 95% of people working in that company has income range from 60 and from 40 to 60,000, because with a 5,000, let's say if you have the mean, if the average is um, $50,000 with a standard deviation 5,000, you see for us on a line, on a normal curve, let's put a normal curve like this. If the mean is 50K, one standard deviation would be 55K, 45K. Two standard deviation, you add another standard deviation, that's 50 plus 10, give you 60K. Minus 10 give you 40K. Thousand, of course. Three standard deviation would give 65K, and here would give you 35K. So if for in any normal curve, Okay, suppose I'm terrible with doing this. Remember that would be right. So for a normal curve like this, what we mean, 68% of people working in that company has, 68% of people working in that company has salary range from 45 to 55. 95% of people working in that company has an income range from 40,000 to 60,000. And of course, 99.7% of people working in that company 99.7 have income range from 35,000 to 65,000. We leave a 0.03% for the CEOs, those people who have just a contract for one day, etc. But that's what it is. Now, the other informations you need to cover in these sections that's very important, probably you would enjoy covered, because there is a lot beside doing this is the coefficient of variations. I believe we did talk about it. We have two examples to cover to finish. Coefficient of variations usually for a set of data non-negative sample of population data expressed as percentage describe the standard deviation relative to the mean and is given by the following formula. So we use this to find the coefficient the coefficient of variations. That's something we don't really talk about. So it helps us to compare variations in different set of data. We can use standard deviation when the data sets use the same units of measures and have measures that are about the same, right? So as we said, for data set with different units of measure or different means, we use the coefficient of variation. So we did a lot of examples like this in a different video. I would strongly advise you to take a look. Round of rule for the coefficient of variation, um, one decimal places, okay? So bias and unbiased estimator, that's something else you need to pay attention to. The sample standard deviation is bias estimator, okay, of the population standard deviation sigma, which means that values of the sample standard deviation S do not tend to center around the value of the population standard deviation. But the sample variance S squared is an unbiased estimator of the population variance sigma square, which means that the values of S squared tend to center around the values of sigma squared instead of systematically tend to overestimate or underestimate sigma square. Right, you see we have two data, I think we did that one before, right? So the only thing they ask you to do here is to find the coefficient of variation for each of the two samples that then compare them. We know how big this is gonna be for us if we do that. Remember the goal, we must find the standard deviation. Once you find, remember the formula is find the standard deviation for each data. Standard deviation you need because coefficient of variation is S over sigma square you divide by 2. So we said coefficient of variation, you must find uh, over x bar and you multiply it by 100, or coefficient of variation because it's samples. We're going to use S. So what we need to do, we can go back in the data we already did. We know what should be the sample because we add up all these data. Okay. If we add up all these data, we can find it. Okay. So let's see where did we do these examples. All right. I'm gonna just use the final answers to Excel because I want to have time to show you how to find the mean. Remember, for the first data, systolic blood pressure right here, X bar, when you add all the data and you divide by 2, X bar was 127.6. If you do the same thing to find the standard deviation S, remember to find the standard deviation S, when you do that, remember the formula to proceed to find the standard deviation, it gave us 18.6. So if you don't find this, now, okay, and for the diastolic, X bar for this one would be, for the diastolic, it is 73.6, and the standard deviation S, after you do all the computation, you must do the computation, 12.5. Now, what is the coefficient of variation? So here, coefficient of variation, we said it's CV, remember is S, which is 18.6 over 127.6. What's coefficient of variations at this one? Of course, you need to multiply it by 100%, all right, 100%. So that means the CV in this case would be 14.6%, okay? And for the diastolic one, you know, coefficient of variation in this case, okay? We're gonna do CV equal the S, what is S? 12.5 over the mean, 73.6 times 100 to express it in this in percentages. CV in this case, for the diastolic one, would be 16.9%. So the variation is roughly about the same, roughly about the same, right? It's very close, roughly about the same. The percentage is very close, all right? So that's what we're gonna consider when they ask you to find the the coefficient of variation of a data set relative to the mean of the data, right? So hopefully you can use this and do the next one. And in a different video, remember, look for the Excel files, because everything we do here, we're not gonna moving forward using doing statistic with our technology. So we would either use calculator, TI-84, Excel, StatCrunch, ScanDisk, etc. So let me know if you have any questions. I'll see you in a different video. Take care.